Okay. Again, a reminder that the homework 7 is due on Friday. And as I've said before, I'm hoping that you'll find it's not quite as time-consuming as the integral problems are concerned. Oh, and by the way, I did put up here, there was a question about this one problem, number 44 in 11.2. And I guess let me put this up here for the other folks here so we can share with them. This is number 44. Anyway, it's asking to find the limit of, if it exists, of this series, which consists of the ln of n over n plus 1. And they do give you a hint to use telescoping sums. So what we want to do here is use our log property here and separate this out. And this, we have an ln of something divided by something, so we can take it, separate it as the ln of the top minus the ln of the bottom. Okay. And therefore, let's look at the partial sum of the first j terms. And so this is going to be basically, for n is equal to 1, we're going to have ln of 1 minus the ln of 1 plus 1, ln of 2. And then for n equals 2, we're going to have the ln of 2 minus the ln of 3. And after you do a couple of these plus, I need to put a plus there, ln of 3, we're going to have ln of 3 minus the ln of 4, etc. When we get to the j term, we're going to have the ln of the number j minus the ln of the number j plus 1. And then if you see here, all the middle terms here will, they say telescoping, will cancel each other out. So all we're left with in this partial sum of j terms is the first term, ln of 1, minus the ln of j plus 1. Okay? And then to look at the limit, then the series limit, we take the limit as this j goes to infinity. And of course, this is going to be, the ln of 1 is 0. And so minus the limit as j goes to infinity of the ln of j plus 1. Well, we know the ln, it creeps up slowly, but it keeps getting bigger and bigger as the argument inside gets bigger and bigger. So this is minus infinity as the limit. So therefore, this is a divergent series through that telescoping. Okay? So anyway, that is problem 44 for this homework that's due on Friday. All right, I misspoke at the end of the last class, so I want to make sure we get this corrected here. We were looking at here was, one of the problems that we had looked at was the sum of 1 over n to the third power as n equals 1 to infinity. Okay, now this is a p-series, and the p-series has this format. The sum as n goes to 1 to infinity of 1 over n to some power p. All right, so the n is what changes. The power stays the same. And we know that if the power p is greater than 1, it converges. And if p is less than or equal to 1, it diverges. All right. So in this problem here that I said, okay, our p here is 3, so p is equal to 3, which is bigger than 1, and I mistakenly said, well, therefore it diverges, and it doesn't. It converges because the p is bigger than 1. Okay, so I wanted to make sure that I didn't lead anybody on the wrong path there with that. I want to look at a similar type of thing here. They're typing a message to me, so we'll see what that is. Let's look at a similar kind of problem, another p-series. This is okay, I'll check that out after I finish this. We have sum equals 1 to infinity of 1 over n to the 1/3 power. This again is a p-series. Here p is equal to 1/3. So 1/3, of course, is less than or equal to 1, so we just know, therefore, that it diverges. Okay. So once we identify whether it's a p-series or not, we look at the exponent and determine whether it converges or diverges. Okay. All right, and I did that one. Okay. Let's see here. There's a question on 11.1, number 55. Let me look this up. And what? And on that one, I had said to use the squeeze theorem. So let's see here. Now I'm going to find out why I said that. Okay. It's certainly going to diverge. Does anybody have a copy of the homework for that's coming up? I just want to, no, the actual sheet of paper, right. Use theorem for number 55. I don't know why I said that. Now I'm thinking about why did I say that. I said that it, so here's the, question. All right, so we have an equals n factorial over 2 to the n, and this is a sequence. Okay, so this is 1 times 2 times 3 times 4 times n minus 1 times n over 2 times 2 times 2 times 2 times 2 times n. All right. So what do we have here? This is all going to be bigger than I mean, you can see it's certainly as the limit, because this is bigger than 1, bigger than 1. Okay. All right. Yeah, I mean, that's what it seems it would do. The limit, it seems like the limit of this sequence would be infinity. All right. So I don't know, my question here, how is the summation of 1 over n not convergent at 2? Brian, I don't understand that question. So you'll have to tell me more what you're talking about. But this one, I don't know. I said use the squeeze theorem, and now I have no idea why I said that. All right. So show me wrong, but I don't know why I said that. For number 55. Because they have a similar thing, I think, here. Oh, wait a minute, we have something here. There's a similar exercise in the book where it's the summation. We have a summation sequence that's like n factorial over n to the n power, and this thing then is n times 1 times 2 times 3 times n all over n times n times n times n. And then these are all going to be, this is less than 1, this is less than 1, this equals 1. This is all less than 1 over n. And then we could use the squeeze theorem because the limit of 1 over n as n goes to infinity is 0. But I don't know why I said it the reverse. Okay. Okay. And what you're talking about, Brian, is that's a geometric. You're talking about a geometric series, right? Okay. All right. All right. So anyway, I don't know why I said that for number 55. So there we go. It appears to be divergent, and we'll just have to leave it at that. All right. Okay. So let's go on then to that finishes up 11.3, the integral test. So what we're doing is we're putting together a bunch of tests that we can use in order to figure out whether things are convergent or divergent. And then the next section, 11.4, gives us some more tools to use. And this is the comparison test. All right. Now, let's look at this series, summation as n equals 1 to infinity of 1 over 2 to the n plus 1. Okay. Now, this thing looks a lot like the summation of 1 over 2 to the n with no plus 1 in the denominator. I mean, it looks very similar to that. And we know that this is a geometric series. The first term is as n equals 1 to infinity. The first term is 1 over 2 plus 1 over 4 plus 1 over 8, etc. And so our A is equal to 1/2. Our first term, our common ratio is 1/2. We know it converges because the ratio is less than 1, and it converges to A over 1 minus R, which turns out to be the number 1. So it looks a lot like a geometric series that does converge. All right. Now, let's note something here. The denominator, 2 to the n plus 1, that's bigger than the denominator of our convergent geometric series. It's 1 bigger than that. So, if something is bigger than something else, and we flip it down into the denominator, so 1 over 2 to the n plus 1 is going to be bigger than or less than, going to be less than, right? Less than 1 over 2 to the n. Using the basic fact that if we're dividing by a bigger number, we get a smaller number, all right? So, therefore, the sum here, so the individual terms are smaller. So therefore, we expect that the whole sum of this is going to be less than the sum of the other one. Thus, in particular, the partial sum, which is equal to the sum from n equals 1 to j of 1 over 2 to the n plus 1, this is certainly going to be less than what the other series converge to. And every time we build onto this, it gets bigger. So this partial sum, it keeps getting bigger, so it is an increasing sequence. Those s sub j's keep getting larger, and it's bounded by 1. It's bounded at the top. So if we have something that's increasing and bounded at the top, we know that it converges. So this summation of n equals 1 to infinity of 1 over 2 to the n plus the 1 must converge. And this leads us to what is called the comparison test. If we can compare the terms of a series with either a known convergent series or a known divergent series, we can reach conclusions about whether this first series is convergent or not. All right? So here's the, let me give you the theorem, and it's actually called the comparison test. Okay. So suppose we have two series. I'll call one of them the summation of a sub n, as n goes from 1 to infinity. The other one the summation of b sub n, as n goes from 1 to infinity, with positive terms. All right. Then, if a sub n, if each individual term is less than the b sub n term, and we know that this summation of b sub n converges. Okay, we know that b sub n series converges. The a sub n we find out is less than, the individual terms are less than the b sub n. Then we can say that the summation of the a sub n also converges. All right. And then we have a flip side to this. If, say, the a sub n is bigger than or equal to the b sub n terms, so now they're bigger, and we know that the b sub n diverge, that series diverges, well, something bigger than is also going to diverge. Then the summation of the a sub n also diverges. All right. So I think it makes pretty good common sense then, just the statement of this. You know, something bigger is going to, if the other thing diverges, something bigger is going to also diverge. If one thing converges, something smaller than that is also going to converge. I do want to point out, though, that this comparison test, it works only with terms that have positive underlying sequence. The terms are positive. Remember also that when we looked at the integral test in the last section, that also worked with only positive functions or positive terms. Okay. We're going to come across something that works with alternating positive and negative in the next section. But I do want to point out that these are strictly for positive terms. Okay. So let's look at some examples here of how this works. First of all, I want to state this. What we're going to compare this to are the things that we know are convergent or divergent, all right? And there are two main series types that we have looked at. So the most commonly used series for the comparison purposes are, well, one is going to be that P series that we just looked at. And again, just to put this down, the summation of 1 over n to a p power, as n goes from 1 to infinity. Again, repeating this, it converges if that p is bigger than 1, and it diverges if p is less than or equal to 1. And then the other type of series that main one we've looked at is the geometric series. That's where we keep multiplying by a common ratio. And so that's represented as some number a times the common ratio r to the n minus 1 power. And we go n equals 1 to infinity. So let me just write out. This starts as a times r to the 0 power, or just a, times a plus a times r to the first power, when n is equal to 2, plus a times r squared, plus etc. And this thing we know it converges if the absolute value of that common ratio is less than 1, and it diverges if it's bigger than or equal to 1. Diverges if the absolute value of the common ratio is bigger than or equal to 1. Okay. So those are the two types of terms we're going to look at. So now let's look at an example here of how this comparison test can work. Okay, we're going to look at the summation as n goes from 1 to infinity of 5 over 2n squared plus 4n plus 3. All right. And the question is, does it converge or does it diverge? Converge or diverge? All right. What we do here is, for comparison purposes, we look at what are called the dominant terms in the numerator and in the denominator. Quote unquote dominant terms. Dominant term in the numerator and the dominant term in the denominator. And by dominant term, what we're really meaning is the term that has the biggest power, the biggest exponent. The term with, how do I put that in the next page? With the highest power. With the highest power. Okay. So in this one, the numerator only has the number 5. So that's what we're going to use. So we're going to compare to the summation. Now in the numerator, all we have is 5. In the denominator, we're going to use the 2n squared, which is the dominant term, has the biggest exponent. And that's what we're going to compare our given series with. All right. Now, what kind of series is this? Is it a p-series or is it a geometric series? It's a p-series, right. So that's the first thing you want to identify, whether it's a p-series or a geometric series. And what is the value of p, Jenna, for this particular series then? 2. P is equal to 2. That's our exponent here. All right. So a p-series with p equals 2, that's going to converge. Since p is bigger than 1, it converges. This 5 over 2 is not going to, it's just multiplying things by a number. It's not going to affect whether it converges or diverges. It's still going to converge. All right. So we're comparing it to a convergent series. Now let's look here at what we have. This denominator here that we have in our given series is 2n squared plus 4n plus 3. Now remember, n is going from 1 to infinity, so n is a positive number. Is this bigger than or less than the denominator of our known convergent series? Bigger. It's bigger than the 2n squared of our known convergent series. So just like we did before, we can flip it reciprocal. That means, therefore, that 1 over 2n squared plus 4n plus 3 is less than 1 over 2n squared. Again, it's the whole thing. Bigger number in the denominator means a smaller number. All right. So therefore, this converges, this summation converges. The terms are all positive, by the way, so the terms are positive. So therefore, this is less than it by the comparison test. Therefore, this converges by the comparison test. Okay? So do we have an idea then of how this particular example works? Look at those dominant terms. Hopefully you can identify whether it's a convergent or a divergent series, and then do your comparison from there. All right, let's look at some more here. This next one we've actually already looked at, but we're going to look at it a little bit differently than before. So this other example, or next one, is this series where it's the summation of the ln of n divided by n as n goes from 1 to infinity. Now, last class we did look at this. We looked at it with the integral test. Because these are positive and decreasing. And we found that with the integral test that it diverges. Okay. So hopefully we're going to come to the same conclusion. Yeah, Jenna?
How do we know about the positive and decreasing?
Well, we've talked about that in the last class, so you can see me after class on that one, okay? I'll just tell you in brief. We found out it is decreasing because we compare with the integral test. We have to find a comparison function. The comparison function is the ln of x over x, and what we did is we looked at its first derivative. Do you recall from Calc 1 how the first derivative tells us whether something is increasing or decreasing? Okay, I don't want to put you on the spot here, but that's what we looked at. If the first derivative is negative, then the function is decreasing. All right, that's the fact that we used. Okay. All right, but here we're going to see what the comparison test can give us. So we're going to compare this. What series do you think we're going to compare it to? We've looked at it before. No, that's the integral test. We're talking about comparison here. This one is ln of n over n. What do you think we might compare it to? One over n. We're going to compare it to 1 over n. We've looked at this summation of 1 over n. This is called the harmonic series. And what have we found out about this particular sum? And this is also of course a p series, where p is equal to the number 1. And we know that this diverges. So this is a known divergent series, all right? Because we have to compare it with something we know. Now, let's look at the ln. The ln of the number e we know is equal to 1. And if the x then gets bigger than e, the ln of x then becomes bigger than 1. All right, or bigger than or equal to 1. So therefore, for x bigger than e, now what is e? 2.717 or 2.718? The ln of x is bigger than 1. Bigger than or equal to 1. So therefore, let's go back, let's do this here, go back to our series then. So the ln of n over n is going to be bigger than 1 over n. Now, n has to be a whole number. We know if x is bigger than 2.718, we're okay. So the whole number here would be 3. That's the next whole number up. So this is for n bigger than or equal to 3. We have that the ln of n over n is bigger than our 1 over n. Okay. And this here doesn't have to start at 1. It's okay for a couple of terms not to work out, but it doesn't have to start at 1. So therefore, the summation of ln of n over n, as n goes from 1 to infinity, then diverges by the comparison test. Here we're comparing it with the divergence series. Okay. So we arrive at the same conclusion as we did before with the integral test, just a different way. Question on that particular one. All right, let's then look at another example. This one's a little trickier. And it's a good one for say, some homework problems. Here we have the summation as n goes from 1 to infinity. Now the numerator is n plus 1. The denominator is n times the square root of n minus 2. Okay. Now, again, we need to look at the dominant terms to see what to compare it to. Look at dominant terms to see what to compare it to. Okay, in the numerator, the term that's dominant is going to be this n to the first power, n. That's going to keep getting bigger and bigger. That's our dominant term. Now, in the denominator, we have, this is n. What does n times the square root of n equals what power of n when we, as a single exponent? 3 halves, right. We add 1 plus 1 half. That gives us 3 halves. So our bottom dominant term is n to the 3 halves power. We don't have to worry about that negative 2. It's the dominant term. Now, how does this simplify using rule of exponents? This is n to the first power over n to the 3 halves power. We're going to subtract 1 from 3 halves, and we still have a 1 half down in the denominator. And in the numerator, we'll just put the number 1. Okay? So this is what we're going to compare it to. All right. So we're talking about the series then, summation of 1 over n to the 1 half power as n goes from 1 to infinity. And this is another p-series. The p here is equal to 1 half. That's our exponent. 1 half is less than 1. So therefore it diverges. All right. So we're comparing it to something that diverges, which means that we hope we can make it bigger than what diverges. Okay? Now let's look here at our denominator here just for a second. Denominator is n square root of n minus 2. And this is our, okay. Is that, okay. For this purpose here, I'm going to go back to this original way to express it as n over n to the 3 halves power. This is n to the 3 halves power. Take away 2. So therefore, it's less than n to the 3/2 power, because we're subtracting off a minus 2. So if I flip this into the denominator, 1 over n square root of n take away 2, I now flip the inequality sign, and that's greater than 1 over n to the 3/2 power. And then, so however, what do we have in our original numerator? Our original numerator up there is n plus 1. Okay. So n plus 1 is certainly bigger than 1. So therefore, when I put that in the numerator here, I can arrive at this conclusion. N plus 1 over n square root of n minus 2, and this is our original term, is therefore bigger than n over n to the 3/2. Actually, I should have put an n here rather than an 1. I'm sorry about that. And of course, this is equal to what we compared it to, 1 over n to the 1/2 power. So sometimes you have to do a little bit of algebra here just to compare it. And so since is everybody okay kind of with this flipping around and how we saw that the numerator was bigger? We saw that the denominator is smaller, so therefore it becomes bigger. And then the numerator, n plus 1, is bigger than n, so the numerator is bigger. Okay, so it's bigger than a divergent, bigger than a known divergent series. So we can say it diverges by the comparison test. All right. Okay. Let's look at, again, another example, just make sure we're getting the idea of this. This one's going to involve a geometric series for a change. So here we're summing 6 to the n power divided by 5 to the n power minus 1 as n goes from 1 to infinity. Okay. Now, our dominant terms in both the numerator and the denominator are these right here. 6 to the n on top, 5 to the n on the bottom. So we're going to compare to the summation as n equals 1 to infinity of 6 to the n over 5 to the n. All right. Well, I think I can rewrite that a little bit differently just to have the same thing. Since they're both to the same power of n, I can just put them as a single fraction, 6 over 5, and then raise the whole thing. Therefore, Jacob Massman asks, what if the numerator is bigger and the denominator was bigger as well? So therefore, the denominator is bigger means that it's smaller, but the numerator bigger means that it's greater than. So Jacob, my answer to you is the comparison test in that case isn't going to help us. And we're leading right up to what is called the limit comparison test, which hopefully will help us. So the comparison, with Jacob's question, basically, and we're going to see this in just a minute, the comparison theorem doesn't always work. We're going to see that, okay? So anyway, this is 6 over 5 raised to the n power. So this is a what kind of series? We keep raising it to a power, a new power. It's a geometric series. Our common ratio is 6 over 5. Now that's bigger than 1, 1 and 1/5. So when the common ratio is bigger than 1, it diverges. So that's a known divergence series. All right. So we're comparing it to a divergence series. Now let's look at the denominator, 5 to the n minus 1. that, of course, is less than the denominator of our known divergent series, 5 to the n. And so when we flip it into the denominator, 1 over 5 to the n take away 1 is going to be bigger than 1 over 5 to the n. Again, smaller denominator gives us a bigger number. And then all we have to do then is add that 6 to the n, which is a positive number. So 6 to the n over 5 to the n minus 1 is bigger than the comparison series 6 to the n divided by 5 to the n. So it's bigger than a divergent. So therefore, it diverges by the comparison test. Okay. All right. Now I'm going to go to something which, as Jacob brought up, the comparison test isn't going to work. And then we'll take a break after that. So here we just want to say sometimes we can't use the comparison test. Sometimes we can't use the comparison test. And here's an example. We're looking at the summation as n goes from 1 to infinity of 1 over 2 to the n take away 1. Okay. All right, the obvious thing that we're going to compare it to is 1 over 2 to the n. All right, dominant terms. So we're going to compare it to the summation, n equals 1 to infinity, of 1 over 2 to the n. And of course, this is a geometric series. Our common ratio is of 1/2. Therefore, it's less than 1. Therefore, it converges. All right? But then we run into trouble here. Since this converges, we want this one to be less than it in order to use the comparison test. But look at what we have. Our denominator here is 2 to the n minus 1. That's less than 2 to the n because we're taking away 1. Then when we flip things over, 1 over 2 to the n minus 1, now it's going to be bigger, it's going to be bigger than 1 over 2 to the n. So this is what we have. We have something bigger than a known convergent series. So we can't use the comparison test, right? We'd like to, but we can't. The comparison test, if it's convergent, it has to be smaller than these terms of the convergent series. Does everybody see then that we can't here in this case? All right. So the thing is, and then we'll break with this, what we use instead, we now try to use what's called the limit comparison test. And why don't we take a 5-minute break and then we'll talk about the limit comparison test that we can use then. try to figure out what kind of series it is. Read off the terms. 1/3, 2/9 plus 2/9. 1/27. 2/81. Okay, see the bottom is going up by 3n. Right. And what they were just asking is a convergence or what? All right. Is it convergent? All right. Oh, and if it's convergent, find its sum. I don't know if okay, so okay, this is, so from here to here, we multiply by 2/3. Okay, right? And it does go back to 1. Okay. They're all coming from 1 to 2. Okay. Now, this is related. If we what section is this in? 11.2, and this is where this 11.2 talks about. The 11.2 talked about the. No, it hasn't talked about the comparison steps yet. If I did this one, this is the one.
Funny you mentioned Jake Maxwell. I used to go to his high school.
Huh?
Funny you mentioned Jake Maxwell. I used to go to his high school.
Oh yeah? Didn't I do? 11.2. I thought I did. Had done 11.2, 11.4 exercises. Yeah. What did I do with that? And it wants us to actually, if it's conversion, it wants us to find the sum. Oh, I know how it works now. Do I give a hint for this one? Oh. Yeah, well, this is how you have to do this, but you have to break it up into two. Oh, thank you. Here, I've got it here. And what number is this? 28. Oh, yeah. I do have, it can be rearranged as the sum of two geometries, and this is the deal. So basically, you put the ones on top here, the ones with the twos on the top here. And so this is I think it's the common ratio is 1/9. And then you have the same common ratio, I think, with each of them. All right? So they're both, so you can figure out, using your formula, you can figure out the sum of this one using your formula, and you can figure out the sum of this one using your formula. Yeah, that's the tricky thing. So look at those hints. Usually I'm not trying to lead you astray with the hints, although I don't know why I said use the squeeze theorem for the one thing. Duh, I don't know. But most of the time I hope that they help. Okay, well, let's get started again here. And we're going to talk about something that can be used here in this particular case. So let me give you the limit comparison test. Here it is. Now again, we have two series, the summation of A sub n and the summation of B sub n. with positive terms. Okay, with positive terms. And we also have, so we have this. If the limit as n goes to infinity of the a sub n term over the b sub n term. Okay, so this is from the underlying sequence. And we look at the ratio, and we take the limit as n goes to infinity. If this equals c, a finite, positive, not zero, positive number, then we have the following that we can conclude. Then, either both series converge, both the summation n equals 1 to infinity and the summation of bn to infinity, either they both converge or they both diverge, one or the other. So the thing is, we again want to look at a known convergent or divergent series to compare it with. Okay. Let's look at, let me put this, so we need to use a known convergent or divergent series to compare it to. All right. Oops, they're all going crazy here. So let's look at this example that we had seen, the summation of 1 over 2 to the n minus 1 as n goes from 1 to infinity. Okay, so what we're wanting to compare it to is the 1 over 2 to the n, the dominant terms. We want to use the summation 1 over 2 to the n for comparison. All right, and we know that this converges. Okay. So what we have to do then, so here our a sub n is equal to our 1 over 2 to the n, take away 1, and our b sub n, for purposes of this theorem, is the 1 over the 2 to the n. So to use this theorem, we have to do the limit as n goes to infinity of a to the n over b to the n. So that's the limit as n goes to infinity of what? Now we're going to have a fraction divided by a fraction. 1 over 2 to the n minus 1 over 1 over 2 to the n. So when you were taking intermediate algebra, they called those complex fractions or something like that. Well, the thing is, when you divide by a fraction, it's the same as multiplying by the reciprocal. So I'll just put that down here just for the heck of it. Dividing by a fraction is the same as multiplying by its reciprocal. It's the same as multiplying by its reciprocal. So this is going to equal the limit as n goes to infinity. Okay, the top part, 1 over 2 to the n minus 1, and then it's going to be times 2 to the n divided by 1. All right. Now, how can I figure this out? Because the top one gets bigger and bigger and bigger, and so does the bottom one gets bigger and bigger and bigger. But remember the trick that I told you guys to use. What you usually want to do is divide by the highest exponent. Divide all terms by 2 to the n, the biggest exponent. All right. So, what that's going to give us then is this. The limit as n goes to infinity. On the top, we're going to have 2 to the n divided by 2 to the n. Put a big line, and then we're going to have 2 to the n divided by 2 to the n minus 1 divided by 2 to the n. We're just dividing everything out. And of course, the top becomes a 1. The bottom, the first term, is a 1 minus 1 over 2 to the n. So what does this go to as the exponent gets bigger and bigger?
0.
Goes to 0. So therefore, this limit is 1 over 1 minus 0, which is 1. All right. So therefore, that is our positive finite number. So we can use the limit comparison test. So we know that summation of 1 over 2 to the n converges. So by, let me just call it LCT, by the limit comparison test, the summation of 1 over 2 to the n take away 1 also converges. Okay. Question about that first example of this limit comparison test. They have to be positive terms. We have to be working with one series that we know diverges or converges, otherwise we don't know what we're doing. And we do that limit. But that's if we can't use the first comparison test, okay? So let's look at another example here. This one's, there are a couple of homework problems that kind of look like something like this. So here we have n equals 1 to infinity of 2n squared plus 3n all over 5 plus n to the 5th power. Right. Comparison test-wise, well, let's first of all let's find the comparison series. Let's do that first. Okay, remember, we need to look at dominant powers at the top and at the bottom. So at the top, we've got our dominant term here at the top is the 2n squared, right? All right. Now on the bottom, we've got this odd square root of 5 plus n to the 5th power. What the dominant, there is a single dominant term here. It's basically going to be, we keep the radical, but we just have the n to the 5th under the radical. Okay. We want to have the term which has the biggest exponent, but in this case, it also happens to be under a radical. So we have to keep that square root radical, otherwise we'll change the problem. All right, so this is our comparison series. So let's kind of simplify this a little bit. This is 2n squared on top. How can I, this is n to the 5th, the square root of n to the 5th. What would be the fraction exponent that that's equivalent to? Yes, 5 halves, right. N to the 5 power divided by 2. So hopefully we remember this, I hope, from intermediate algebra. You put the power on top. This is how I teach you. You put the power on top, the root on the bottom. So the power is 5, that goes on top. The root here is a 2 because it's a square root that goes on the bottom. All right. And so then let's just use rules of exponents here. So this is the summation of 2. Now, we have 5.5, of course, is 2.5. So what's 5.5 take away 2 for our new bottom exponent? Because we're going to subtract the 2 from the bigger one, the 5/2. It's 1/2. 5/2 minus 2 is 5/2 minus 4/2, and that's 1/2. So just using rules of exponents, our exponent here at the bottom is a 1/2. So this is our comparison series here by using the dominant terms. Now this is the p-series. And in this case, p is equal to 1/2. So therefore it diverges. Since p is less than 1, it diverges. All right. So we're comparing it to a divergence series. Now, the thing is, what we have here, we can't use the regular comparison test. Because notice the numerator is bigger because we have a plus 3n. The numerator would be bigger than our comparison series, right? You see that? But notice the denominator also has a plus in it. So the denominator is also bigger, which means it would be smaller then. So we can't use the comparison test when we have two pluses like that in the top and the bottom. So we need to revert to the limit comparison test. Do we see that we can't just say that we can't just say that 2n squared plus 3n over the square root of 5 plus n to the 5th is either bigger than or less than our comparison series. We can't reach any conclusion about that because we have a plus on top and a minus and a plus on the bottom also. Okay. So we're going to use what's the limit comparison test, and we hopefully will be able to have luck with that. All right. So I need to look at the limit as n goes to infinity of that a sub n over b sub n. So our a sub n then is from our original series, so that's, okay, we've got a big kind of crazy looking fraction here. Our a sub n is 2n squared plus 3n divided by the square root of 5 plus n to the 5th. That's all in our numerator, divided by our comparison term, which is 2 divided by, oops, where's our comparison term here? Here it is, 2 over n to the 1/2 power. All right. All right, so again, we've got the deal where we're dividing by a fraction. So we're going to multiply by the reciprocal. So this is 2n squared plus 3n over the square root of 5 plus n to the 5th times the reciprocal of the denominator. All right. You say, well, gee, I'm afraid things aren't quite so clear yet either. Well, let's do a little distributing here. Let's distribute this n to the 1/2 with those two terms that it's multiplying and see what happens. So 2n squared times n to the 1/2 power, when you add the exponents, that's going to be back to 2n to the 5/2 power, plus n times n to the 1/2 power, so that's going to be 3n to the 3/2 power. And it's all going to be over 2 times the square root of 5 plus n to the 5th. All right. Okay, we're still going to use our same old trick. We're going to divide all the terms by the biggest power of n. In fact, by n to the 5/2 power. Right. Biggest power. Okay, and let's see what we get here. So this is going to be the limit as n goes to infinity. Now this is going to be 2n to the 5/2 divided by n to the 5/2 plus 3n to the 3/2 divided by n to the 5/2 all over 2 times. Now here we're dividing, so this is 2 times 1 over n to the 5/2 times the square root. Okay. What happens here, I want to bring this under the radical, yet not change the expression. If I'm going to bring this 1 over n to the 5/2, I'm going to multiply that and get that under the radical. Let's look at, what do I need to do to the power of the 5/2 if I want to move it underneath the square root radical?
As 1 of the square root of 6.
Actually, so you're suggesting we take the square root of the 5/2 then. Is that what you're suggesting?
No, I'm saying that you would express it differently. Just write it. Wouldn't it go inside of it?
Yeah. Okay, Janet said and Nelson said we'll square it, actually. Let's just look at something here and maybe something a little bit simpler. Say we have 2 times, something without even any numbers in it. Say 2 times the square root of 5. And for some reason, I want to bring this 2 under the radical. To do that, I have to square it. So therefore, I have my radical, I have to square it to get a 4 times the 5. And that gives me the square root of 20. So when we bring something under a square root radical, we have to square it to get the equivalent thing. Does that make sense? All right, so let's see what we get here. The top looks horrible, but it soon simplifies. N to the 5/2 over n to the 5/2, well, that's just 1. So we have a 2 there. And then here, n to the 3/2 over n to the 5/2, well, we just subtract our exponents, and that gives us 3 over n, I believe. 5/2 minus 3/2 is 2/2. So it's n to the first, over 2 times the square root of 5 over n to the 5th. So when we square n to the 5/2 times n to the 5/2, add the exponent, that gives us a 5th, n to the 5 power. This is and then plus n to the 5th that we already had, and that'll also be divided by the n to the 5th. Now, on homework, I know you guys aren't going to be going through all of these particular steps as in excruciating detail like this, but this is the process. So we have 2 plus 3 over n on top. On the bottom, we have 2 times 5 over n to the 5th, and then this other second term simplifies to 1. So by doing this then, now we then look at what happens when n gets bigger and bigger. Well, 3 divided by n, that term is going to go to 0. 5 over n to the 5th, that's also going to go to 0. So what we're left with then is the 2 on top. We did have a 2 on the bottom times the square root of 1. So our limit then is just 1. All right. So we had to go through a little blood, sweat, and tears to get that the limit is equal to a positive finite number. Therefore, we can use the comparison test. So what did we figure out? We figured out that the other series diverges. So since the sum of 1 over, what was the other, 1 over n to the, 2 over n to the 1/2 power diverges, then our original series diverges. And again, this is by the limit comparison test. Okay. And actually that ends that particular part then. Remember that whole trick on doing these limits is dividing by that biggest power of n, so that a lot of stuff then zeroes out and you can find your limit. All right? Okay, so that's the two tests that we found in that section, the comparison test and the limit comparison test, and they both require positive terms. All right? Now what we're going to go to in the next section is alternating series, 11.5. We'll get a start on this one. And here is where some of the terms will alternate between positive and negative. Yes, Shanna?
I have a question. So when we had on the bottom of the last problem, we had 1 over n.
What's n to the 5/2 times n squared? What's n to the 5/2 squared?
Well, 5/2 squared is 25 over 1.
When you, here, I've got it right here. N to the 5/2, and we're squaring it, okay? When you take a power to a power, what do you do with these exponents? You multiply them together. So this is equal to n times 5 over 2 times 2, which is n to the 5th power. Or you could have done it this way. You could have just taken n to the 5/2 times itself, because that's what you do when you square it. And here you would have to add the exponents together. 5/2 plus 5/2 gives you n to the 5th. Okay? All right. Now we're going to look at series that alternate, the terms alternate between positive and negative. Between positive and negative. So I'll show you a couple of examples here. Here's a series that starts out with a 1, then we subtract 1/2, then we add 1/3, then we subtract 1/4, then we add 1/5, etc. Okay. This is actually represented then as follows. Our denominator is just going to be the number n, because notice it goes 1, 2, 3, 4, 5. And on the top, and we have a 1 on top, but we have to account for the fact that we alternate in sign. So this is what you see with these series. You have in front here, you have a -1, and then we take it to the power. So notice this thing starts out as positive. When n is equal to 1, it's positive. So what power do I need to raise -1 to get a positive number? Yeah, it has to be squared. So this thing has to be written as -1 to the n plus 1 power. So when n is equal to 1, -1 is -1 squared, which is a positive 1. When I go to the second term, n equals 2, we have -1 to the 3rd power, which is the -1, which is what we have there. So you see this -1 raised to a power to indicate the alternating between the minus and the plus. Another example of this is, say, -1/2 plus 2/3 minus 3/4 plus 4/5, etc., like this. Again, we're alternating between positive and negative. The way that we can write this is this. Okay, now notice here, if we're starting at n equals 1, these terms begin at the number 2. So this would have n plus 1 in the denominator to indicate, because when n is 1, we get 1 plus 1 is 2. Now in the numerator, though, we start at 1, 2, 3, 4, so the numerator would just be the plain n. And then I also have to account for the minuses and pluses. Now this time, so we have a minus 1 in parentheses. This time, though, the first term is negative. So I'm going to put, if I put minus 1 to the n power, that'll give me, when n is equal to 1, I'll have minus 1 to the 1, which is minus 1. When n is equal to 2, I'll have minus 1 squared, and that'll equal 1. I want it to be positive for the next term. All right. So these are two examples of alternating series. Now we have, just like we have a comparison test and a limit comparison test, we've got a test to see whether an alternating series converges or not. And it's called the alternating series test. And this is the principal fact of this section here. Alternating series test. And I'm going to call it for short AST. All right? So here it is. If the alternating series and here we have it, a summation, say, of n equals 1 to infinity of minus 1. We'll start it off where it's positive, so we'll put n minus 1 here. So it'll start positive. It doesn't matter as long as it's alternating, whether it starts positive or negative, of Bn. So this Bn is a positive number, and we're multiplying it either by a minus 1 or a plus 1, okay? So if I want to write this out of the first few terms out, when n is equal to a 1, we're going to have a positive b sub 1, b1, because it's minus 1 to the 0 power. And then when n is equal to 2, we'll now have a minus b2, because now it's minus 1 to the 2 minus 1 power, which is equal to minus 1. And then it'll continue this way, plus b sub 3 minus b sub 4, etc. Okay, again, it alternates. So if we have an alternating series such that these b terms keep decreasing, the b sub n terms keep decreasing, i.e., b sub n plus 1 is smaller than the one before it, smaller than b sub n. They keep decreasing, and not only that, the limit as n goes to infinity of this bn is equal to a 0. So not only are they decreasing, but they're going to 0, then the series converges. And I know I didn't do it, but I should have put asterisks by that limit comparison test, because that's obviously something you're going to be responsible for. All right. What I want to show you here is just a little slide which kind of shows you how this works. So, PC all. And let's see, where is it here? All right. This is, I scanned this from the textbooks. So these are our B terms here that we keep adding and subtracting. So notice here, and they're positive. So notice we have our B1, which is biggest, and that's a positive term. And then we're subtracting from it, because they alternate in sign, then we're subtracting from it the B2 term, but it's smaller, so we're not going all the way back. And then we add to that the B3 term, but that's still smaller, so we're not going all the way back again. And we continue this process where now we're subtracting the B4 and then adding a smaller B5, subtracting a smaller B6, and then this stuff starts wiggling back and forth here and gets smaller and smaller, and finally these all sum up to a single finite number. So again, if they alternate in sign and these B's keep getting smaller and smaller and they're all decreasing, then we meet the test and the sum is a finite number. It converges. Okay? All right, let's just see if we can get a couple of examples in here of this test. Let's look at this one here. The sum as n goes to 1 to infinity. Now right here we have our -1 to the n minus 1. That kind of thing is your clue that you have an alternating series. All right? And then that's being multiplied by 1 over n. So what this thing looks like then, if we just look at the first few terms, the first term is going to be a positive 1 over 1, or 1. Then we're going to go negative 1 over 2, positive 1 over 3, minus 1 over 4, positive 1 over 5, etc. All right. These terms here, 1, 1/2, 1/3, 1/4, 1/5, those are the terms of that harmonic series, right? Where we have 1 plus 1/2 plus 1/3 plus 1/4. So this is called, because it's alternating in sign, this is called an alternating harmonic series. All right. Okay. And let's see if we can use this test here to see whether it converges or not. Okay. So first of all, we have to see, is Bn plus 1 less than the preceding term? Well, yes, it is, because we have our Bn plus 1 is 1 over n plus 1. It's strictly the positive part of it, and that is certainly less than 1 over n, because this is a bigger number, bigger denominator. So we can check that we meet that. And of course, the B terms are all positive. Now let's look then also at the limit as n approaches infinity of the Bn. So that's the limit as n goes to infinity. Our Bn is 1 over n. One over the 1 here. Are you talking about right here? Right there? Let's see. N plus 1 is bigger than n, right? So therefore, when I go to the denominator, 1 over n plus 1 is less than 1 over n. What did I do? You have less than and less than? Well, yeah. Okay. Yeah, all right. In this case here, what is our Bn here? Bn is equal to 1 over n. See, our terms are 1, 1 over 1, 1 over 2, 1 over 3, 1 over 4. So our Bn is right here. Our Bn is 1 over n. So B sub n plus 1, if we just plug in an n plus 1 here, b sub n plus 1 is 1 over n plus 1. All right? Are we okay with that? So, b sub n plus 1, which is 1 over n plus 1, that is smaller than the preceding term b sub n. Because b sub n is just 1 over n. So I do want to have, because we want the next term to be smaller, and it is, because the next term has a bigger denominator, so it means when we flip it over, it's smaller. Okay, all right, okay. Now, going back then to the limit here of these b sub n, well, that's the limit of 1 over n. Well, as n gets big, as our denominator gets bigger and bigger, this limit is equal to 0. So that is the second part of what we want, that the limit has to equal 0. So therefore, we can apply the alternating series test, and if we've met all the criteria, so therefore it converges by the alternating series test. So what's kind of interesting, to me at least, what's kind of interesting is this. We've known that, or we've been told that the limit of 1 over n, where we don't change the sign, this is that harmonic series, that diverges. And of course it's the p series where p is equal to 1. That diverges when we don't change the sign. But for the alternating harmonic series, as n equals 1 to infinity, that's the alternating one, that does converge. All right. So I think that's an interesting little fact. A little factoid or something like that. All right. Yeah. All right. We have time for one more example of this alternating series test. So this is what we want to look at here. The summation minus 1 to the n plus 1 power, so that's our clue, we got an alternating series, times n squared over n to the third plus 1. And we want to find out if it converges or not. Okay. Now, remember, we have to have b sub n plus 1 has to be less than the preceding term. That's to meet the criteria of the test. Now, it's not immediately evident to me. Yes, Jenna?
Is this a problem?
Is what?
I thought you said we were applying this.
You said what now?
Only criteria that we needed, and then you said we need to apply the test, but we didn't apply it.
Are you talking about the last problem? We met the two criteria, that the limit of the b sub n's is equal to 0, and the other one was where they're decreasing, b sub n plus 1 is less than bn. Those are our two criteria, so I can therefore just say that it converges by the alternating series test. All right? Okay. I tell you what, this is all leading up to one section, which is a whole strategy for dealing with these series. And if you don't do the homework, you're going to find yourself overwhelmed by too many tests. You know, I mean, if you don't do the homework and get used to these tests, you're going to say, you're going to suddenly be faced with, because you're not going to be told on a test which test to use. So if you're not, so just kind of I'm getting up on my pedestal about doing the homework, and so I don't want to get too carried away with that. Okay, so the thing is, this isn't real obvious to me that b sub n plus 1 is less than the preceding term. So how can we figure this out? Well, let's look at the corresponding function. Let's look at, instead of n squared, let's look at x squared, and instead of n to the third plus 1, let's look at x to the third plus 1, and let's look at its derivative, and see if it is less than 0. Because if it's less than 0, then it is decreasing. All right? So we have to use the quotient rule. And so we square the denominator. That's going to be x to the third plus 1 squared. All right? And then what is this? The denominator times the derivative of the numerator. So that's x to the third plus 1 times the derivative of the numerator, 2x, minus the numerator, x squared, times the derivative of the denominator, 3x squared. Okay, let's FOIL things out and see what we get there in the numerator. The denominator, is the denominator going to be a positive or a negative number? Always positive because it's a square. And we're talking about here, we're talking about x bigger than or equal to 1. Okay, let's distribute this. We get 2x to the, what is that? The fourth power, x, 1 plus 3 is 4, plus 2x times 1, minus, and then we multiply these together. This is 3, x squared times x squared is x to the fourth. Now let's combine like terms. 2x to the fourth minus 3 is going to give me minus x to the fourth plus 2x all over x third plus 1 squared. And then this thing here, minus x to the fourth plus 2x, we want this to be less than 0. And that's going to occur, let's add x to the fourth to both sides. So when 2x is less than x to the fourth, or dividing by x, when 2 is less than x to the third power. So therefore, as long as x to the third is bigger than 2, this is a decrease, this is a negative derivative. All right. So I think that's, so as long as x is bigger than the cube root of 2, when I do the cube root of both sides, this is then f prime of x is a negative number, less than 0. All right. So therefore, we don't have to, so therefore, for 2 and up, we're okay. Because the cube, I don't know what the cube root of 2 is offhand, but it's 1 point something. But so therefore, we're okay, because the derivative we found out is negative, then our terms decrease in value. Everybody all right with that? Just looking at the derivative. Thus, I can say Bn plus 1 is smaller than the preceding one. Okay. Then the next thing we have to look at is the limit of b sub n as n goes to infinity. Okay, that's the limit as n goes to infinity of what? Okay, our Bn here is n squared over n to the third plus 1. All right. So what do I want to do here to check out this limit? What's the trick? What power of n? Biggest power. It's best to just go on and just use the biggest power. You could use n squared and it would work, but I just want to just give you a consistent thing to do and just divide by the biggest power of n. So divide all terms. Jenna, you would see that it would work if you divided everything by n squared, but let's just divide all terms by n to the third power. So this is going to give us the limit as n goes to infinity. Okay, the top one's going to be n squared over n to the third, then over n to the third over n to the third, plus 1 over n to the third. All right, let's simplify this. The limit as n goes to infinity. Now, n squared over n to the third, that's going to simplify as 1 over n. And then in the bottom, the first term, n to the third over n to the third, that's going to be a 1. And then 1 over n to the third. So as n gets bigger and bigger, this top term goes to 0. And this term on the bottom also goes to 0. So our limit then is 0 over 1 plus 0, which is 0 over 1. So our limit is 0. So we've met both criteria of the test. The limit of the bn's goes to 0, and they are decreasing. We looked at the first derivative. So I can say thus converges by the alternating series test. Okay, right. All right, we'll stop there then. In fact, we'll just do another couple examples of this next time, and that'll finish the alternating series test, and we'll go on then on Friday. So we'll finish up with another example of alternating series test, but then we have a couple more tests that we're going to learn in the next section. They're called the ratio test and the root test. So and those are the last two that we'll have. So you see we're going to have about a half a dozen or 5 tests or something like that to look at to see whether something converges or not. That's a bewildering class. Thanks, Sam, I think. Okay.